Hello, we are CTU Robotics, a student team from the Czech Technical University in Prague. We would like to present to you what we have prepared for this year's European Rover Challenge. Our team is a multidisciplinary group of over 40 students, learning and working together to build advanced robotic systems for space exploration. The main goal is to connect and shape the next generation of engineers. The team is organized into specialized departments of about 5 members, each led by a department leader. These leaders form the CTU Robotics board, overseeing all activities. The Chassis and Robotic Arm department designs and builds the rover structure, suspension, mast and robotic arm with various grippers. Electronics and Communications department manages power systems, control electronics and rover communication. The Autonomous Systems department develops navigation, sensing, data processing and autonomous control. The Science department is a team of 8 chemistry and space geology students focused on planetary research and sample analysis. Drone department builds aerial systems for mapping and collaborative rover drone missions. And finally, our marketing and PR department shares our work and story through public engagement and media.
Perun Gen 2 is our second-generation planetary rover. During construction, we aim for robustness, driven by the proverb, "Get things done." The sturdy chassis feature a rocker bogie suspension with 6 driven wheels, of which 4 are steerable. Base mobility offers forward, backwards, and in-place rotation movements. The sides are decorated with the sensing mast, providing vantage points for our cameras and communication antenna, drilling shaft for deep sample collection, storage system to support onboard sample analysis, and a robotic arm. Structures are primarily made from aluminum profiles and custom CNC machine components. Additionally, thanks for the sponsorship of our partner Prusa Research, we have heavily utilized 3D modeling and printing of the rover's inner structures. Our distribution, computation and communication units are kept fully enclosed in an adjustable inner frames layout. For safety, the rover relies on 2 mechanisms: hard-coded software limitations and system status prevention that evaluates the current and future state of the rover. In case a set of predefined rules gets violated, the safety unit either dispatches the halt command or cuts the power to the rover. Additionally, the design offers the hardwired emergency stop switches located atop the chassis that directly cut the power lines to the drivetrains, rendering the system completely still.
On the software side, we split everything into 2 logical segments: the ground segment and the rover segment. Inside the rover segment sits an Ethernet backbone with a layer 7 switch at the networking core. This backbone links all the peripheral devices, sensors, controllers and radios to the central computing hub. The application layer is handled by the ROS2 framework on the central computing hub and lightweight C++ nodes on the peripherals. The distributed network reaches the ground segment through 2 independent uplinks: Wi-Fi Halo and LoRa. On the ground segment, our ground station hub runs a monitoring stack comprised of Grafana, Prometheus and Loki, and our own backend application. Backend application serves a web-based control dashboard to the operator over the local network. This infrastructure gives each one of our subsystems room to evolve independently. On the control side, the rover offers 2 locomotion modes, Ackermann and point turn. The Ackermann offers forward and backwards mobility and side rotations according to the center point moved from the left or to the right. Point turn offers only the side rotations with the center point at the center of the rover. In case of emergency, our computational unit can cut the movement through hard-coded limitations, or we can press an emergency button on the rover. The rover's autonomous control is provided by the Visual SLAM. Inputs for the Visual SLAM are 4 cameras, IMUs and wheel encoders.
Our drone department closely cooperated with another great product of CTU, Multi-Robot Systems, the absolute experts in their field. Together, we have developed our drone Jarilo. Jarilo's brain consists of a powerful Intel NUC commanding Bighawk 6X flight controller. This setup allows for fully independent onboard computing and fully autonomous operations. Its eyes and ears consist of a LiDAR for indoor navigation, fused together with stereo vision and visual inertial odometry to allow for all scenario GNSS denied navigation, both indoor and outdoor. For mission control, we use a MATLAB mission controller for image processing and high-level decision-making. The drone operator can monitor operations through an RVIS panel, and backup manual control is available via a radio controller. Safety is our top priority. The drone features an emergency auto-land function activated by fail-safe conditions, such as signal loss or critical errors, ensuring safe returns in all situations. The result? A drone ready for autonomous takeoff, waypoint navigation, and precise landings, all fully integrated with our rover mission. Our custom 6° of freedom robotic arm is designed for precision and power. It can lift up to 3 kg and features a modular maintenance gripper with interchangeable 3D printed fingertips. With embedded pressure sensors, it allows delicate manipulation of objects. A dedicated end-effector camera with object detection allows the arm to identify interface panels, buttons, and probes. This enables both autonomous panel interactions and autonomous probe retrieval. The probes are safely stored in a custom container integrated into the rover's chassis.
Our science team is made up of 8 students with backgrounds in geology and chemistry. We take an interdisciplinary approach to tackle the complex challenges of planetary exploration. For this year's competition, we've chosen to focus primarily on the mineralogical study of our designated Martian region. Studying the mineral composition can reveal insights into the area's geological history and help us identify potential biosignatures or other signs of past life. To support this focus, we've equipped our rover with 2 advanced instruments: the Metro Mira XTR Raman spectrometer for in-situ mineralogical identification, and the Advocam Minipix, a compact radiation camera that can also contribute to mineral characterization and environmental assessment. Both systems are co-developed with research institutions and tested in field-like conditions. For surface sampling, a robotic scoop collects regolith and rock into a compartmentalized science box for weighing and secure transport. To explore below the surface, we use a custom-built drill designed to reach depths of over 30 centimeters. Finally, we've also been preparing for the astrobiology task with a dedicated team member focusing their research on biosignature detection and environmental conditions that might support life.
We've learned so much about robotics and ourselves through this project. It challenges our thinking and, most importantly, lets us connect and share our journey with the international community. None of this would be possible without the incredible support from our mentors and sponsors. Thank you and see you in Krakow!